Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, Overpressure Protection and the Relation to Regulations, Codes, and Standards. Our speaker is Justin Phillips. Justin Phillips has over 7 years of onshore and offshore oil and gas process engineering and project execution experience. His technical experience includes process design with specialty in flare and relief systems. Justin holds a BS in chemical engineering from Texas A&M University in College Station, Texas. He is a licensed professional engineer in the state of Texas. One quick note before I turn the session over to Justin Phillips. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Justin Phillips. Hi, Justin.
Hi, Pam. Thank you. Good morning or good afternoon or good evening to all of our audience members. We appreciate your time today in watching this webinar. A lot of thanks go out to AICHE and also Pam Benson for helping get all of this coordinated. So thank you very much, Pam. For today's presentation, obviously we're going to talk about overpressure protection, but really what we're going to talk about is how overpressure protection and the work that we do is related to regulations, codes, and standards. So the purpose of today's webinar is that you in the audience, if you don't already have familiarity with kind of the relationship between the work that you do on a daily basis related to pressure relieving systems or to just process technology in general, if you don't know how that's related to industry standards, how it's related to codes of construction that we use in our industry, and how all of that is related to regulations, I'm hoping that by the end of this webinar, you at least have kind of a picture that kind of ties all of those things together so that at least you can be a little bit more informed and be able to draw from today's experience in the work that you continue to do. And when I talk about our industry, total and complete full disclosure here, this webinar, as some of my previous webinars have been, is really tailored to those in the audience who work with pressurized system, who work with pressurized equipment, who do work in the hydrocarbon sector, be it upstream, working in production, working on a production platform, or working midstream, or working downstream in a refinery or a petrochemical complex. This is really who this webinar is tailored to, but that being said, there are still other parts of kind of the chemical engineering industry in general that you would find application. Okay, so the big picture, kind of the overview of how we're going to do this today, we're going to take a high-level view of regulation, codes, standards, and practices. We're going to start with what I believe is probably the most familiar kind of territory, which is the internal, kind of the internal standards that you might have in your company. And then from there, we're going to kind of work our way upwards to industry standards. And then from industry standards, work into codes of construction. And then from codes of construction, make our way into regulations that are kind of controlling our industry. Towards the end, we're going to put it all back together. So we're going to go through all of this, go through the big picture, work our way up through all of these different types of documents. At the end, we're going to put it all together. We're going to have a review and then maybe kind of a quick example of how these things get tied together. We're going to go over a couple of definitions. So some of you have probably seen this before. It looks like, before I continue, it does look like we may have lost sound from a couple of attendees. I'm not sure if this is a common problem for all attendees or just some attendees. I'm going to go ahead and continue to go on unless there is a reason for me to stop, and I'll just let Pam work in the background to check on this.
Hi, Justin. Sorry. Let me just interrupt for a second. No, we still have sound. If anyone does lose sound, though, they should log out of the webinar and back in, and it should come back.
Okay, thank you, Pam. So looking at the definitions, I do apologize if some of you can't hear me, but this slide at least, even though you can't hear me, I'm just going to read kind of verbatim what's on the screen. API, I think a lot of us know what API is. API is the American Petroleum Institute, and it's an organization that really promotes policies that are favorable for the U.S. oil and gas industry. So API is it's an organization, right? But its members are those members who are involved in the hydrocarbon sectors here in the United States. And API has a big lobbying branch. Most of what it does is lobbying. But also API is responsible for a lot of the standards that we have in industry, how to operate equipment, how to run equipment, how to maintain equipment, how to do all kinds of stuff. And so API is kind of a go-to for industry standards. ASME is the American Society of Mechanical Engineers. It's not an organization there for profit or anything, but its general purpose is to promote engineering knowledge, to promote the sharing of that. ASME, a long time ago, was kind of responsible for putting together the codes of construction that we use in our industry today, be it for powered boilers or be it for pressure vessels. That is the organization which is responsible for a lot of the codes of construction that I'm going to reference today. The term code is a rule that describes kind of the application, construction, protection of equipment. Regulatory compliance, which we'll talk about in a second, is often based on the code. Codes of construction often tell us exactly and precisely how to build equipment. Like with a pressure vessel, it's going to say, you shall build this piece of equipment exactly this way. You're going to weld it exactly like this. You're going to put nozzles on it exactly like this. You're going to calculate MAWPs exactly like this. It's really stringent, not stringent, it is stringent. It's really prescriptive, which is another term. It's really prescriptive on how to build stuff, but it's not so prescriptive when it comes to protecting it. So for instance, ASME Section 8 says, you shall build this vessel exactly like this. And by the way, you shall protect it. It doesn't tell you how to protect it, though. So then we kind of move into consensus standards. So consensus standards is what I use to describe any sort of industry standard that was developed through kind of a big group discussion and agreement among whoever in industry is involved in that consensus. It could be owner-operators, it could be manufacturers, it could be people from academia, it could be private industry like consultants or engineering firms, things like that. OSHA, which most of us here in the United States is familiar with, is the Occupational Safety and Health Administration. It's part of the U.S. Department of Labor. OSHA is what enforces and polices industry compliance with its regulations. So for instance, the PSM standard, 29 CFR 1910.119, OSHA is kind of the policeman that makes sure that everybody that falls under that regulation follows that regulation. There's a term called performance-based, and there's another term called prescriptive. These two terms, they're not opposites, but it's important to know the difference between the two. A performance-based anything, a performance-based standard, it kind of tells you what the end goal is. You should eat healthy. Okay, it's not telling you exactly how to eat healthy or what exactly you should be cooking to eat healthy. It just says you should eat healthy. Prescriptive is kind of the step-by-step way of achieving your end result. So if performance-based means that's your end goal, prescriptive means that it's the exact way to get to that end goal. So to meet performance-based requirements, you often have to use some sort of prescriptive step-by-step way of doing something. PSM. I think a lot of us know what PSM stands for, but for those of you who don't, PSM is Process Safety Management. RAGAGAP. RAGAGAP is a very important legal term. We throw it around all the time nowadays. It stands for Recognized and Generally Acceptable Good Engineering Practice. It sounds kind of like a mundane 1, 2, 3, 4, 5, 6, 7 letter acronym, but it has pretty significant legal significance because OSHA treats the term RAGAGAP as something that's enforceable. A regulation is a law, so compliance with a regulation is your responsibility. You've got to follow the law in whatever you do. Last term, standard, it's just a common way of describing how to do something. We kind of talked about consensus standards earlier, but not everything is developed by consensus. So just standard by itself is just how you do something. So looking at the big picture, like I said, we're going to start with familiar territory first. We're going to start with internal standards and then work our way to consensus standards and then work our way to codes of construction and then finally to regulations. So an internal standard is something that you usually get on the first day of the job. Like you walk into work, 30 minutes with HR, an hour with HR, whatever, and then you go to your supervisor and your supervisor says, here you go, here's a stack of internal standards. Please be familiar with them within the next week. So they generally contain, broad statements like this is how we do business, and they may contain very explicit statements like this is exactly how we do our business in this sort of situation. Consensus standards are kind of a big general set of how-to statements, and it's developed by industry consensus. Codes of construction are these things that tell us exactly how to build equipment, and in this case, in pressure relieving systems, they tell us that we shall protect it, but not exactly how to do that. And then finally, we have regulations that we're going to talk about. Regulations is the law, and these are the things that tell us the documentation that we require in order to show that we have compliance with the law. So talking about internal standards, still just general overview of internal standards. Internal standards could also be called company standards. Are the company's internal policies that might cover the gamut of like really, really high-level compliance with whatever, like performance requirements, all the way down to calculatory, like this is exactly how you do this in this precise way of doing it. And we find that often the bigger or larger or older companies usually have the biggest sets of standards and probably even have places where their internal standards are more stringent than the generic industry practice. So moving on to consensus standards, the consensus standards come from collaboration between industry entities. So like your company plus another company plus other companies that all kind of care about one particular thing. They work on that common theme and they work towards a goal of how to provide, how to do something in particular. API Standard 521 is a really good example of an industry consensus standard. And it's places where different companies, different entities have found that common ground and kind of agreed how to identify, for instance, how to identify overpressure scenarios. What are the standard overpressure scenarios? What are the general ways of disposing of relief loads? I think the consensus standards are fairly prescriptive as far as they can possibly get away with. They're going to tell you exactly how to do something to the point that consensus can be reached. So not everybody agrees exactly on every single step on how to do something, but they probably agree on a lot of it. And so those exact agreements, those exactly how to do something, those are written down in those consensus standards. Also, industry consensus standards are considered by OSHA to be RAGAGAP. So moving on up to codes of construction. So codes of construction, like specifically those from ASME, like the boiler and pressure vessel codes, they were developed by manufacturers and they're enforced by government authority to reduce accidents and loss of life. That's how they came about. The rules for overpressure protection are generally performance-based in ASME Section 8 with a few kind of prescriptive directions. So where we had internal standards, which might be really prescriptive, where we have consensus standards, which are a little bit less prescriptive, but still prescriptive, we run into codes of construction, which are not terribly prescriptive. They're just kind of more performance-based. They say you shall protect this piece of equipment. And finally, moving back to the top are the regulations. So the regulations, as I said, those are the law, and those within the jurisdiction of this law must comply with the regulation. I think in my experience, and this is why I'm kind of putting this together and sharing this with the audience today, is that I think that these are kind of the least well understood in our industry because we get so bogged down with the daily grind, with the internal stuff, getting stuck in the weeds. We may lose sight, or we may not have sight of at all with kind of the higher level regulations. So I think that the common engineer may not be as familiar with this, and so that's why I wanted to talk about it today. And an example of a regulation could be a state boiler law or a state pressure vessel law. Another example would be the 29 CFR 1910, which is a federal regulation which affects the United States, like all of the United States. And these regulations are very often performance-based. They give you the end goal that you need to meet and doesn't tell you exactly how to meet that goal. So moving in into the next part of the presentation, we're going to work our way upwards. We're going to look at this. Looks like a stack of pancakes, making me pretty hungry. We're going to look at this stack of pancakes. We're going to start on the bottom, and we're going to work our way up. So starting at the bottom, the biggest part of the pancake is kind of these internal standards, followed by the industry consensus standards, followed by codes of construction, then finally into regulations. So let's just start there and work our way up. Internal standards. So those are the ones that are developed and implemented by your employer for its own business purposes. What is the purpose of an internal standard? I think a lot of people have a pretty good idea of what it is, but I think the best way of kind of putting it into concise words is to say that your internal business practices are these pragmatic, repeatable approaches that lead to success or satisfies one of your business needs, and they do it in a consistent way. So somebody that started the business wrote down or recorded how they did something that led to success, and so that they could share it with the next person and the next person and the next person, so that success could be repeated and so the business could continue to grow and make money. I think that makes sense, right? Also, these are ways there are ways to have success. There are also ways to avoid failure, business failures or accidents or, injury, things like that. So it's ways to succeed and ways to avoid failure. So kind of the history of internal standards, if we think back to, not that we could think back because we can't possibly be this old, back to the turn of the century, back in the late 1800s and beginning of the 20th century, there was, there's boiler works, there's lots of boilers being produced, there's, we're starting oil production, we're starting refining, all of this industry is proliferating, and so this is all new technology, this is new industry, these are new horizons, and as the industries grew, they faced some really new and complex challenges, like how do you make higher pressure steam? How do you do things like that? How do you refine this petroleum into something that's usable? So how could these boiler producers make boilers that were safe to operate and wouldn't blow up and kill people all the time? People had a lot of issues. There was, dozens, if not hundreds, probably even more than that. I don't even know I'm saying a number. There's so many accidents related to boilers blowing up and killing people that it really started to catch the attention of the public, the government, and industry. So as companies grew and they continued to grow and they failed, other people picked up on those failures. The companies picked up on those failures, and they started to write down their own practices. They started to really record what was successful and what should be avoided. And as companies grew and merged or acquired, all of these internal practices, they kind of mutated and they went through time and became what they are today. But typically, those internal standards stay internal. They stay internal to the company, and they're locked down. Nobody else outside of the company really gets to see them. So as some of you know, your internal standards could be really, 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 really big or really, really short, and it depends on the complexity of the business. Very large organizations have internal standards that could be hundreds or thousands upon thousands of pages long, whereas smaller businesses, maybe they only need a page or two, or maybe a few pages. Really depends on the company's size. Internal standards, these are often like when you're working in office, these internal standards are the law of the land as far as your business is concerned. These tell you what to do and how to do it. Because companies do have kind of this interest in doing good business that is legal and that people don't feel kind of weird about doing, people generally trust their internal standards to be right, to be lawful, to be sound, to make sense. And so usually a lot of people don't move outside of their internal standards. If they cover what you need to do on a daily basis in your work, you don't need to look anywhere else except for your internal standards. And the most ideal internal standards are the ones that are so fully encompassing that they cover everything that you could possibly ever want to do, from sizing a relief device to considering the fire case scenario on the tube side of an exchanger to how to procure a stapler, how to order business cards. They cover everything. Why do they cover everything? And the reason here is because, one, they may cover everything because the business is so old that they've just developed the best way of doing something. But the other reason is that we can't always rely on outside sources like industry standards or codes or other things to tell us how to do everything. There's vagueness and there's ambiguity in some of those external things, and so we rely on our internal standards to cover the gaps. So even though internal standards, like ideally, are fully encompassing, they cover everything, that is rarely achieved without extensive effort, extensive money, extensive time and energy, and just extensive focus. The other reason it's kind of hard to achieve this fully encompassing internal standard is that the industry changes all the time. It's a moving target. But thinking about that as a moving target, like API standards. API standards change, maybe once every 5 years or so. People have to hit this moving target, and so they may not spend the time in focusing on getting these internal standards ready, only to have to change them every 5 years, right? So some companies will spend the time and the money to have these fully encompassing standards, so that they can always have an answer. But at the same time, if they're spending that amount of time to have these fully encompassing standards, they're probably also protecting themselves by lobbying the things that change in industry. So businesses want to protect themselves. They want to protect themselves and their investments from any sort of thing that's going to cost them more money. So companies will get together and they will lobby at the regulation level. For instance, companies that are members of API are sort of represented by API at the regulation level, because API will lobby Congress to do certain things. And companies also lobby at other levels to maintain a status quo. And it's a way to make sure that that industry target, that moving target, doesn't move so much, and it's a way of limiting how much time and money they'd have to spend when things do change. But doing that, lobbying and spending the effort there, is really expensive. And that's why typically we find internal standards are not fully encompassing. They cover the necessities of the business, but they otherwise don't cover everything. So just thinking about this as an example, imagine you work for a small refining business with limited resources. There's not a million process engineers at your disposal. There's not a ton of lawyers. There's not a ton of support staff. You've just got what you need in order to make a buck. And so as far as overpressure protection is concerned, maybe your company has one particular way of doing some scenario, but otherwise they say, this is how we do this one scenario. Everything else, use the industry standard. And whenever when an interpretation issue arises, because say that there's ambiguity in those consensus standards, then you might hire a consultant from the outside to solve it one time, and that's it. So you're limiting the amount, because you have limited resources, you're therefore limiting the amount of money that you spend on solving problems, and you solve them as you need to. So internal standards with respect to overpressure protection, this kind of goes back to where we talked about kind of boiler works proliferation, as well as refining proliferation at the end of the 19th century, beginning of the 20th century. We saw lots of accidents, right? So lots of loss of life. It got everybody's attention, and so something had to be done. To protect people and equipment, ASME, which was composed of industry participants, sat down, came up with ways to build boilers that would stop exploding, and also how to protect those boilers. So these participants, which were from private industry, kind of came together. They found common ground. They developed a code that bettered the entire industry. It protected people, protected equipment. The environment probably wasn't too much of a concern then, but maybe it protects the environment as well. And so the code was written in such a way that it made it easy for manufacturers to build safe boilers. It made it easier for people to know how to protect them, how to build them, how to maintain them. And it also made it easy for the authorities, like state governments, to make sure that people were following those rules. So speaking of private entities sharing their internal knowledge for the betterment of industry, this is a really good segue, because it brings us into the consensus standards. So consensus standards are the result of all of these entities getting together, lending their internal knowledge, finding common ground, and solving problems that are common to all of them. So as the industry started to develop and follow the requirements of the ASME codes, it left some questions of exactly how to meet the requirements. And I'm specifically talking about pressure relief systems. So ASME code says, install a relief device. Okay, what kind of relief device? How do we size it? What do we consider? Things like that. Because of that, API became sort of over years and years and years, became the go-to organization for developing the prescriptive how-to part of that equation. We know we need to protect ourselves, but how do we do it? API has developed numerous standards. It's more standards than I can count on my fingers and on my toes, and also recommended practices, over decades and decades about how to meet the requirements of code. So each of these standards usually covers one facet. So for instance, API 520 Part 1 tells us how to size, and API 520 Part 2 tells us how to install. and 521 tells us which overpressure scenarios to consider and what we should do with the relief effluent. But it is worth mentioning that API is not the only organization that provides guidance on overpressure protection. Indeed, AICHE DIRES, which is the Design Institute for Emergency Relieving Systems, is another really well-regarded organization. It's recognized for its contributions to our industry. They are big on knowledge exchange. They're big on the development of techniques and formulae, which are acknowledged by API. So two-phase sizing equation, things like that, that wasn't put together by API. That was put together by people that got together and formed DIRES a couple of decades ago. And just as a quick sidebar, for those of you that are going to be going to the AICHE Spring Meeting and Global Congress on Process Safety in Austin next week, DIRES will have a booth at the meeting. So if you're there, by all means, please stop by, get to know a little bit more about DIRES if you don't know anything already. So even though like these consensus standards may come from various sources, the common thread between them are the participating members. And this is, I'll get into it in just a second, but this is where I think another, like, hey, FYI, this is how this works. I think this is where some of you in the audience will start to recognize, wait a minute, API doesn't just make this stuff up themselves. Somebody else that's a member of API is putting this together. Anyway, we'll get to that in a second. But think about that as things change, as the industry evolves. We are, in the hydrocarbon sectors, refining has been around for 100+ years, and offshore production has been around for, 50, 60, 70 years. We are not so calcified in the way that we do things and nothing ever changes. We are always building. We're always developing new technologies. We're always throwing out old technologies. And so because of that, we have to develop our standards to make sure that it keeps up with how our technologies and how our industry is changing. This is that moving target phenomenon that I was talking about earlier, and it's this reason, this moving target, which drives participation from the companies that are involved with consensus standards. So, I mean, the discussions in these consensus standards meetings are pretty interesting, but the changes that occur because of the changes in consensus standards do have real tangible impacts on business. Some of you may, when I say API 526 valve, some of you, they may immediately make sense. You know what I'm talking about. All of these generic API-sized valves. Let's say if I was to tell you that's a 4M6 with a 150-pound flange. The face-to-face dimensions on this PSV are standardized throughout the manufacturer. So you could go to manufacturer A, B, or C. All of them probably offer what's called an API 526 valve that is interchangeable as far as its geometries are concerned with any other manufacturer. And the reason for this was because people and users were tired of having to replace valves, going to another manufacturer and having to repipe their systems because the dimensions didn't match. Now, when this standardization of sizes came about, it did cost money because the manufacturers may have had different sizes for their castings on their valves, and now all of a sudden they have to offer a common size. Now they have to develop new castings. Now they're going to charge you more money to have these valves and to sell them to you. So any of the changes in the standards do have real impacts, and that's why people want to stay on top of these changes. So, okay, this is what I was talking about a minute ago. Earlier in my experience, I had no idea who or what API was. I just knew that I got this piece of paper that says API standard 521 or 520 or whatever. I got it. And I just imagined, oh, API put this together. That entity put it together. It's not just some nebulous person at API that puts it together. The fact is that its members put those together. And so the next question is naturally, well, who are the members? And I didn't realize any of this. The members are probably the companies that some of you work for right now. If your company has anything to do with the hydrocarbon sector, be it an owner-operator, be it an engineering firm, be it a private consultant, your company is probably a member of API. And your company probably had a hand in making changes or discussing those standards. So why do the standards change and how often do they change? So as I said previously, technologies change. They just do, and we have to keep up with it. So for pressure relief systems, the API Subcommittee on Pressure Relieving Systems, which is made up of manufacturers and owner-operators and consultants and you name it, they meet twice a year, and usually the schedule for things to be released is about every 5 years. So about every 5 years, you should probably expect to see a change in the standard. A lot of the standards, 520 Part 2 was recently re-released in its new edition, so 5 years from now, maybe a new edition. Same thing with 521. You should probably see something in the next 4 to 5 years. So consensus standards are valuable tools that help the users work through the nitty-gritty, how do I do this? But in some cases, they also provide the basis for that regulatory compliance. Remember the term RAGAGAP. OSHA recognizes that there is recognized and generally acceptable good engineering practice in those standards, and so OSHA treats RAGAGAP the same as it would code. So that's pretty important, and that's pretty significant. So for instance, this 3% rule, which by the way is in a non-mandatory section of code, ASME Section 8 Appendix M, is also found in a consensus standard, API 520 Part 2. So for those of you familiar with the 3% rule, OSHA has a laser focus on this right now because even though it's maybe non-mandatory in the Code of Construction, it does look like something that is RAGAGAP inside of a consensus standard. So the break between code and standard can sometimes be fuzzy, maybe for this reason alone, that OSHA may treat it the same way. But I do, for the intent of this webinar, let's just say code. I'm going to use ASME Section 8 as my code that I'm going to talk about today, and I'm going to talk about the API standards as my standards. So the big difference is that, remember, code says, in this case, for pressure relieving systems, code says for overpressure protection, you shall protect it. Just satisfy that requirement. And the standard says this is how you satisfy that requirement. Like a consensus standard, the codes of construction were also developed by consensus, as we kind of discussed earlier. But the big difference is that the codes of construction are, drum roll, older, established, edified, codified. They're older, right? And if something has been written and it's been there for a long time, people generally tend to treat it with a little bit more respect. They treat it as something that's been there, it's established. That's something that we should trust. Codes are not really subject to drastic changes. And they're also developed in such a way that their performance-based nature lends itself to ease of enforcement by regulatory bodies. So any of us, any professionals in this audience, or any professional that spends any length of time working on PSVs, pressure relief systems, will probably run across ASME Section 8 requirements in their work. But in my experience, it's been that exposure to ASME Section 8 and those requirements is often self-limited. And why is that? Well, just thinking of ASME Section 8 Division 1 alone, that's 800 pages long, which, you know, everything is super lengthy, but like to get into that, to think about 800 pages and how to process that, it's kind of scary and it's daunting. So people see 800 pages, ugh, forget that, and they move on. And the other reason is because standards like API 521 or whatever, they're written in kind of a simple, more actionable way. Whereas the codes may not be written in such a way that's, you know, something that is not as easy to understand. You've got to sit there and you've got to stare at this 2-sentence paragraph and spend 15 minutes trying to understand exactly what it means. But do not fear ASME Section 8. Just because it's 800 pages long does not mean you should fear it. Doesn't mean you should run away from it. You shouldn't fear ASME B31 or ASME Section 1 either. The codes are daunting, but if you focus on the pressure relief requirements, it makes it a lot easier to digest and a lot easier to internalize. So if you're working on release systems right now and you're not familiar with ASME Section 8, B31, ASME Section 1, there's some key segments that you should really focus on. It's easy to go through, it's easy to read, and at least you'll be familiar with where these requirements are so that you can use it in your daily work. So on ASME Section 8, you can take a note. Sections UG 125 to UG 140 is the perfect place to start, read, understand, and internalize those things. Also Appendix M, which is a relatively short appendix. By reading those specific sections, you can quickly understand why we do certain things, like why are there certain rules that we see in the consensus standards. So for instance, looking at UG 125C2, and this is the verbiage here is also repeated later on in UG 130 or 133, don't quote me. It says, when a pressure vessel can be exposed to fire, the pressure relief device shall be capable of preventing the pressure from rising more than 21% above MAWP. Like, whoa, bam, right there. That is the code requirement that tells us 21%. So you've always been told, hey, 21%, 21%, 21%. Why? Because it's right there in the code. That's where it came from. I think there's also some pretty good additional hidden gems in ASME Section 8. For instance, UG 127, it's a section that talks about non-reclosing pressure relief devices. Part D, Part 1 says that flow paths or vents open directly or indirectly to atmosphere may be used as the sole pressure relieving device. So what's that saying? What that is saying is that if you've got, and it seems kind of obvious, if you just have an open piece of pipe that goes to atmosphere, okay, yeah, that can be a relieving device. But what's really cool is that you can imply from this that if you have an indirect path to atmosphere, say like a piece of pipe that is part of your cooling water header, which eventually goes to atmosphere, you can use that piping segment, that hydraulic network, as a relief device. So it gets you away from necessarily having to install a PSV or a rupture disc or whatever. So if you thought a PSV was the only way of doing something, that's not true. That's not necessarily true. And so by reading these, these short sections in ASME Section 8, you can open your eyes to see the other possibilities. Definitely a comprehensive review of all the code requirements for overpressure protection is not in any way possible for this webinar, but I would encourage the audience to kind of look at these different sections. For Section 8, look at those, UG 125 through 140 and Appendix M. ASME Section 1 is listed there. B31.3, that particular section in 322.6.3 is also pretty cool. Going through these and being able to regurgitate code requirements is the perfect icebreaker for any cocktail party and any social gathering. I promise you, you will be the life of the party. Moving on up, working into regulations. So regulations are the law. This webinar will focus particularly on one regulation, 29 CFR 1910.119, which is a mouthful, and it's short. It's another way of saying the PSM standard. It's a federal regulation, which means it covers the entire United States. It's enforced by OSHA. It also covers a lot of facilities, but not every facility. It covers any facility with a hazardous material in excess of 10,000 pounds, but it does not cover production platforms. It doesn't cover certain storage facilities. But the things that you find in the PSM standard are often the things, the elements that make up the PSM standard you often find in these excluded facilities anyway. So even if you work on an offshore platform, you're not subject to this, you probably will find some of the elements that we're about to talk to being complied with in your facility regardless. So OSHA put together the PSM standard back in the early 90s as a way to, as a kind of a response to notable big giant accidents. There was a Bhopal disaster in India in '84. There was Phillips Petroleum had a plant. There was an explosion and fire which killed a bunch of people in 1989 here in Texas. And the intent of the PSM standard was to make sure that facilities which handle hazardous material do it in a safe, consistent, and measurable manner. Make sure everybody is at least meeting a certain bar, a certain threshold of safety. So there's a bunch of different elements. I'm not going to read them off, but there's one on here which I think is the most important. That's my opinion, and that's process safety information. And if you look at these elements, the relationship between these elements in the regulation, training, contractors, trade secrets, they are not entirely clear. You kind of think, how do I relate that to one of the standards of the code that we were talking about before? Because these things have such innocuous names. I'll tell you, we'll get into that. So process safety information, which I think is the most important, is a term that doesn't really click with everybody in the audience. I think some of you, if I say the term PSI or PSM, some of you that work in a refinery or a similar facility, you automatically know what that is. It makes images of PSIP matrices come to your mind. It makes you think of PNIDs. It makes you think of all sorts of stuff. But if I say it to somebody else that works for, an engineering company that is not a refinery, it might not mean anything. I mean, it sounds like English. It looks like English, but otherwise it doesn't mean anything. And the reason it doesn't mean anything is because the PSM standard doesn't apply to everybody. And if it doesn't apply to your business, you may not even care about it because it's not applicable. It's not a business necessity. So process safety information, what is that exactly? What does that even mean? Specifically, what process safety information means is that you have information on your process chemical hazards, toxicity, reactivity, corrosivity, thermal and chemical stability data, the kind of information that you would find on an MSDS. It also includes information on the process technology, which may include a block flow diagram, your process chemistry, maximum intended inventories, and safe operating limits for temperatures, flows, compositions, whatever. And also an evaluation of what happens if you deviate from normal operations. Now, the next part of process safety information is very near and dear to me. So it's information on the process equipment, materials of construction, piping and instrument diagrams. This is one of my first true loves in the industry is P&IDs. I'm sure a lot of you out there love P&IDs as much as I do, but I love them. This is like, oh, P&IDs are great. I love P&IDs. Electrical classification stuff, I'm not so big on that. I don't have an electrical engineering degree. Release system design and design bases, super important to me, obviously, but also super important to some of you out there. Ventilation system designs, design codes and standards employed, also super important. Heat and material balances. This is probably the first true love of any chemical engineer because one of your very first classes in chemical engineering was how to do heat and material balances. That is considered process safety information. And then also safety systems like interlocks, suppression systems, stuff like that. So real quick, for any process engineers, chemical engineers out there that are working at engineering companies that don't necessarily know what PSM is, you don't care about the PSM standard, you've never heard of it before, I want you to know that those P&IDs, the heat material balances, and all of those relief device calculations are crazy, 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 crazy important. They are so important. They don't go into a black hole at the end of a project. They don't just disappear. When you're done with that, that deliverable is turned over to satisfy your client's regulatory compliance needs. And one last bit on PSI, process safety information, is that it also says that you shall document that the equipment that you're designing complies with REGGAP. So putting it all together, we're going to do a quick review and then a quick example. So starting from the bottom, company policies are those internal standards. Moving up a little bit higher, if we need to move away from our company policies, we take a look at consensus standards. What does everybody else in the industry do in order to meet compliance? And then moving a little bit higher, why do we need to meet this compliance? What is the basis? Codes of construction, like ASME Section 8. And then what is the regulation? What do those things come from? 29 CFR 1910-119. So let's have an example. Surprise, you are being audited by OSHA. Sometimes these audits are true surprises, in which case nobody is happy, but oftentimes OSHA audits are known. You see them coming down the road. If your facility is a VPP star, you probably have a VPP star audit schedule, and so you know when to expect OSHA to come in. So the team of OSHA inspectors come in and they want to take a look at your PSM system. And one of the inspectors is focusing on 1910-119, and they want to know about the PSI related to your relief system design basis. So the inspector goes to your relief systems engineer, and she says, do you have any PSVs with an inlet pressure drop exceeding 3%? And your relief system engineer clears his throat, and he says, well, yes, we do have some PSVs with inlet pressure drop exceeding 3%. And some of you may be gasping, like, oh my gosh, I bet he's going to get in trouble. Oh, he's in trouble. That's not necessarily true. So intrigued, that inspector, she digs a little deeper, and so she's like, okay, I want you to show me all of this information. I want to see your U1A forms. I want to see your PSV nameplates. I want to see your overpressures that you came up with. I want to see the calculated rates. I want to see your required orifice sizes, and I want to see those pressure drop calculations. Not a problem. So your relief system engineer provides all this information to the inspector really rapidly because, no worries, your PSM system is really, really robust. So the equipment nameplate and U1A forms, you got it. This is the ASME Section 8 code requirement. You got it on hand and easy. PSC nameplate, same thing. This is a code requirement. You got it. A list of overpressures, easy peasy because your release system design basis covered all of the standard scenarios that you see in API 521, and it probably covered the other stuff which is specific to a particular process. Your relief rates and your required orifice areas, yep, you got that too because you calculated everything based on API 520 Part 1. You quantified your relief rates using the help of API 521. And then your inlet and outlet pressure drop calculations, you've got that as well. It's very well documented. So the inspector, she takes a look at this information carefully, and she's like, you know, everything looks right, but this inlet pressure drop, you're right, it does exceed 3%. Can you show me an engineering analysis that this pressure drop is acceptable for these PSVs? The audience gasps. Oh no, what's going to happen? So because your release system engineer is always on top of the industry and is always prepared for situations like that, he's already prepared based on the latest edition of API 520 Part 2, Section 736, write this down, audience, 736, which spells out how to perform an engineering analysis. It tells you what to do for those valves that are already installed if you need to consider if the valve is going to be okay if its inlet pressure drop is calculated to be greater than 3%. So your release system engineering analysis shows a preponderance of evidence that the current pressure drop that's above 3% is okay. So the OSHA inspector, she's satisfied, she's happy, she claps her hands, and she leaves. And then you give your release system engineer a nice bonus because he totally killed that situation. And that concludes the webinar, and now we're going to move into Q&A. Before I start the Q&A, every question that is asked, if you use the Q&A box towards the bottom of the screen, Pam is going to get a copy of all of those questions. Anything that we are not able to get to today, we will include those questions and the answers in the kind of the final published version of this webinar, which is going to be in a PDF. So if you have a question and we don't answer it, go to the webinar once it's published in a few days, go towards the bottom of the PDF, you're going to find the questions and the answers there.
Okay, thank you, Justin. First question. In order to project a new process for which it doesn't have any specific regulation or standard, how can I make a good formal safety review and put my process on an ISD state?
That's a pretty complex question. So if there's no particular regulations, kind of sounds like a, not to sound sexist, but it sounds like no man's land, no person's land. I would be curious to know where this particular process is going to go. If there, in lack of, let's say there's a complete lack of regulation, either by a state or by a country or some sort of federal anything, the next thing that you would move down to would be, in my opinion, should be the codes of construction and any practices which are employed in order to meet the requirements of the code of construction. That's the first thing I would do. There were some other parts of that question which sounded which I missed some of them, but they sound a little bit more complex. I will make sure that I address all parts of that question in the published webinar. But good question, thank you.
Great, thanks. Will you mention those codes, for example, ASME 8, which are incorporated by law?
Yes, so I think as part of the end of this, I can list out kind of generically all of the ASME codes of constructions for quick reference.
Okay, excellent. Please direct your questions to host in the chat box. Does the 3% rule apply to ASME Section 1 equipment?
The answer to that is, so ASME Section 1, for those of you that aren't familiar with ASME Section 1, Section 1 is for power boilers. And it's written differently than it is for Section 8. With power boilers, when it comes to overpressure protection, there is no specific mention of inlet pressure drop requirements at all, none. But there are other things. You just have to make sure that your valves have adequate capacity and that your allowable accumulation does not exceed 6%. That being said, if you can imagine your PSV having an inlet pressure drop of 3% on a Section 1 vessel, you might not have the valve stability that you really desire, and you might not be able to protect your vessel at the required limitation on allowable accumulation. So with ASME Section 1, the 3% rule does not apply. You should probably have a lot less than 3% inlet pressure drop.
Okay, thank you. Are you familiar with any overpressure protection codes or regulations specific to high-pressure lab scale experiments?
That is a very good question, and unfortunately, I am not. But to kind of satisfy what we're going to publish, I will take a look and see what I can find.
Okay, great. Do international shipping containers built to ASME Section 8 have to follow the overpressure protection requirements in ASME Section 8?
So for international shipping containers, often there is, even though the vessels may be constructed with accordance to ASME Section 8, the overpressure protection requirements are not necessarily the same. I don't remember the different codes or standards or whatever the regulations are for those shipping containers, but they can be different than the requirements of ASME Section 8 because ASME Section 8 may not be applicable as law in international shipping.
Okay, thank you. For an ASME code stamped pressure vessel, when can pressure relief be omitted?
So this comes from, you can read more about it in ASME Section 8, non-mandatory Appendix M, but also I think inside the code itself, there are certain situations where you have overpressure protection by design. A good example, and it has to be documented, you have to have documentation from the manufacturer's report, which is the U1A form, that says that overpressure protection is not required because there's nothing that can cause an overpressure. Let's say that the fire, let's use generic, block outlet case and fire case. Let's say that the source of whatever is filling your vessel, it can't possibly hit the MAWP. Well, block outlet doesn't apply. And let's take a look at fire. Let's say that there's no possible source of external fire or some weird external heat that could possibly get you near your MAWP. In cases like this, you have overpressure protection by design because your vessel is built sturdy enough that it doesn't require a PSV to protect it because it's protected intrinsically.
Okay, thank you. Is the 10% rule in code?
Okay, so the 10% rule, it's not, so 10% is with respect to, there's kind of two ways you could see this. 10% rule could be with respect to your allowable accumulation. So if you have a single device protecting a vessel, like ASME Section 8 vessel, your allowable accumulation is going to be 10%. Unless you have multiple devices, then it's 16%. And if you have a fire case, then it's 21%. So that part of this quote-unquote 10% rule is spelled out in code as allowable accumulation. But as far as not exceeding 10% for different types of devices, like a conventional valve, you shouldn't exceed, and this is where it gets kind of confusing, you shouldn't exceed the allowable, your outlet pressure drop should not exceed your allowable accumulation for conventional devices because of a force balance equation, your valve could shut or cycle.
Okay, thank you, Justin. Anything you'd like to say in closing?
Not particularly. I do love the questions. If I do see some questions that are being asked in the chat box below, and I'm not sure if we're going to have time to get to them today. However, if you do have questions, please do continue to send them in. We'll make sure that all of them do get published in the webinar I guess the final version that we publish in a couple of days.
Right, and I would ask if people are sending questions to presenter, please send them to host so that I have a record. We did get a question because we've answered most all the questions, but we did get a question in while we were just speaking, and we have a minute or two, so I'm going to ask this to you. Justin, can overpressure protection by design be applied to an existing vessel not originally designed for that scenario?
Ooh, tricky question. So the requirements of code, I believe, are written in such a way that you could probably get away with this if you get a new manufacturer's report which says this. However, anecdotally, I have heard of some cases where overpressure protection by design has been implemented for existing things, for existing systems, where there are plans to implement this and plans at the same time to get an updated manufacturer's report.
Okay, excellent. So if you do have a question that you felt was not answered today, please send it to producer@aiche.org, and I will forward it to Justin. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Justin Phillips for this very informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this webinar or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.